The James Webb Space Telescope found something so ancient that it has left cosmologists using words like terrifying and no going back now. A primordial galaxy that appears to have formed when the universe itself was barely 200 to 300 million years old, so close to the Big Bang that it challenges the very timeline of cosmic evolution. This is not just another high redshift galaxy. It is a fully formed system with stars, heavy elements, and structure when the universe should still have been in its chaotic dark infancy. This is galactic origins, and over the next several minutes, we will examine this extraordinary discovery in exhaustive detail, the crisis it has created in cosmology, the possible explanations, and what it means for our understanding of the birth of the universe itself. The galaxy in question, provisionally named in the 2026 data releases, has a redshift so extreme that its light has been traveling for more than 13.5 billion years. When the light we see left this galaxy, the universe was only a few % of its current age. What makes this object truly shocking is its maturity. It is not a tiny chaotic clump of gas. It shows clear signs of organized star formation, chemical enrichment, and structural development. Features that standard models said should take billions of years to appear. The discovery has prompted one leading researcher to state publicly, "There's no going back now. The universe we thought we knew is gone." Let's be precise about what JWST actually observed. The galaxy exhibits strong emission lines indicating active star formation. Its spectrum shows the presence of heavy elements like oxygen, carbon, and nitrogen far earlier than models predicted. It also appears to have a compact but organized structure, possibly an early disk or bulge, when the universe should still have been dominated by population 3 stars. These observations directly contradict the standard hierarchical formation timeline that has been the backbone of cosmology for decades. This single galaxy is not an isolated anomaly. It joins a growing list of high redshift objects that appear too mature for their age. Together, they are forcing cosmologists to confront the possibility that our understanding of the cosmic dawn is fundamentally incomplete. This discovery represents more than a new record. It is a turning point. The James Webb Space Telescope has pushed our view so close to the cosmic dawn that the universe we see no longer comfortably fits within the framework we built over the past half-century. And that realization is both deeply unsettling and profoundly exciting. Let us be very precise about what the James Webb Space Telescope actually observed in this primordial galaxy. The object, detected in one of the deepest 2026 survey fields, has a redshift so extreme that its light has traveled for more than 13.5 billion years. When this light began its journey, the universe was only 200 to 300 million years old, barely out of the cosmic dark ages. What shocked astronomers is not just its distance, it is its maturity. The galaxy already contains significant populations of stars, active star-forming regions, and, most surprisingly, clear spectral signatures of heavy elements such as oxygen, carbon, and nitrogen. These metals require multiple generations of stars to produce through fusion and supernova explosions. According to standard models, there simply had not been enough time for this level of chemical enrichment. In the research labs, this discovery caused immediate excitement mixed with disbelief. One 2026 research paper summarizing the findings states, "The presence of significant metal lines at such high redshift implies that star formation and chemical evolution proceeded at rates far exceeding current theoretical expectations." The galaxy is not a tiny, chaotic proto-galaxy. It shows hints of organized structure, possibly an early rotating disk or dense central bulge, features that models said should take billions of years to develop. This single object compresses what was supposed to be a slow, gradual process into a few 100 million years. According to the standard hierarchical model, the first stars should have formed around 100 to 200 million years after the Big Bang. These stars would then need multiple generations to enrich the gas with heavy elements before more complex galaxies could form. The entire process was expected to take 1 to 2 billion years before galaxies reached the maturity we see in this object. JWST has compressed that timeline dramatically. The universe was still in its infancy, yet this galaxy already looks like a teenager. The implications extend beyond this one galaxy. It joins a growing population of high redshift objects that show the same pattern of premature maturity. Together, they suggest that the early universe was far more efficient at forming stars, enriching gas, and building structure than our models allowed. This is why one leading researcher publicly stated, "There's no going back now. The data is too consistent. The discrepancies too systematic. We cannot simply adjust a few parameters. We must reconsider fundamental assumptions about how the first chapters of cosmic history unfolded." This single primordial galaxy is not just an interesting outlier. It is a direct and severe challenge to the standard model of galaxy formation. In the standard hierarchical picture, galaxies build up gradually. Tiny dark matter halos merge over time. Gas slowly cools and collapses. The first stars form, explode as supernovae, enrich the gas with heavy elements, and only after billions of years do we get the kind of mature, chemically enriched galaxies we see today. This object compresses that entire multi-billion-year process into a few 100 million years. That is an enormous compression of cosmic timescales. The problems are multi-layered. First, there is the mass problem. Forming a galaxy with hundreds of billions of stars requires an enormous amount of gas to be converted into stars in a very short time. The efficiency required is far higher than what standard models allow. Second, there is the chemical enrichment problem. Heavy elements don't appear magically. They are forged in stars and dispersed by supernova. Seeing significant metal lines at such high redshift means multiple generations of stars must have already lived and died, something that should have taken far longer. Third, there is the structure problem. The galaxy shows hints of organized morphology, possible disks or bulges, features that require time, angular momentum, and dynamical relaxation to develop. In research labs, this galaxy, and others like it, has created what many are calling a genuine crisis in early universe cosmology. The standard model is not just slightly off, it is systematically underpredicting the pace and efficiency of structure formation in the first few 100 million years. This is not something that can be fixed with a small parameter tweak. It points to something missing at a more fundamental level. Let us pause for a thought experiment. Imagine the very early universe, only 200 million years after the Big Bang. In a particularly dense dark matter halo, gas collapses at an extraordinary rate. Star formation explodes in a burst far more intense than anything we see today. Massive stars live fast, die young, and seed the gas with metals almost immediately. Dynamical processes quickly organize the system into a proto-galaxy. The entire process that we thought took billions of years happens in a cosmic blink. This is what JWST appears to be showing us, and it is forcing theorists to explain how such extreme efficiency was possible so soon after the Big Bang. This discovery is so disruptive because it strikes at the heart of our timeline for cosmic evolution. If galaxies like this are common, then our entire narrative of how the universe went from a smooth plasma to the complex structured cosmos we see today needs major revision. When a discovery this disruptive arrives, the scientific community does what it does best. It searches for explanations. In 2026, researchers are exploring a wide spectrum of possibilities, from relatively modest adjustments to the standard model all the way to radical new physics. The most conservative approaches focus on boosting star formation efficiency in the early universe. Perhaps higher gas densities or stronger feedback mechanisms allowed galaxies to assemble faster. These tweaks can alleviate some tension, but many researchers believe they are not sufficient to explain the full set of observations. More ambitious ideas are gaining traction. One popular candidate is early dark energy, a component that was stronger in the first few 100,000 years after the Big Bang. This could have accelerated the growth of density fluctuations, allowing galaxies and black holes to form more rapidly. Another avenue involves self-interacting dark matter. If dark matter particles can scatter off each other, it could alter how small structures collapse and merge, potentially solving both the early galaxy problem and some small-scale tensions seen in local observations. Some researchers are even exploring whether fundamental constants, like the gravitational constant or fine structure constant, varied in the early universe, fundamentally changing the pace of cosmic evolution. The most radical proposals go even further. Some theorists are revisiting cyclic or bouncing cosmology models, where our Big Bang was not the absolute beginning, but a transition from a previous cosmic aeon. Let us explore this idea in more depth through a thought experiment. Imagine the universe is cyclic. Each aeon expands, cools, and eventually reaches a smooth, low-entropy state. Through some mathematical rescaling of space and time, that end state becomes the hot, dense beginning of the next aeon. In this picture, our Big Bang was not creation from nothing. It was a transition. If this is correct, the primordial galaxy JWST discovered might not have formed entirely from scratch. It could carry subtle imprints or seeded structures from the previous aeon, allowing it to mature much faster than expected in a single-cycle universe. This would elegantly explain both the rapid structure formation and the surprising chemical enrichment. It would also align with the sense that we are looking at a different universe, one with a much deeper history than a single Big Bang allows. The discovery of this primordial galaxy, and others like it, marks a genuine turning point in cosmology. The James Webb Space Telescope has pushed our view so close to the cosmic dawn that the universe we see no longer fits comfortably inside the framework we built over the past half-century. The phrase "there's no going back now" perfectly captures the moment. The data is too consistent, the discrepancies too systematic, and the implications too profound to ignore. We are no longer fine-tuning a successful model. We are confronting the possibility that key assumptions about the birth and early evolution of galaxies, stars, and heavy elements may need to be fundamentally re-examined. This is not a crisis of failure. It is a crisis of opportunity, the kind that historically leads to the biggest leaps forward in science. Just as the discovery of dark energy in the late 1990s forced us to rewrite the story of cosmic expansion, JWST's early universe observations may force us to rewrite the chapter on how structure first emerged after the Big Bang. For all of us watching from outside the laboratories, this discovery carries a deeply personal resonance. We are living in a privileged moment in human history, a time when we can peer closer to the birth of the cosmos than any previous generation, and see that reality is far grander, far older, and far more surprising than we imagined. This primordial galaxy reminds us that the universe was already building complexity when it was still a toddler by cosmic standards. It challenges our timelines, humbles our assumptions, and reignites our sense of wonder. In a very real sense, it tells us that the story of the universe is still being written, and we are lucky enough to witness a new chapter unfolding. The James Webb Space Telescope has shown us strange and wonderful things. It has challenged our models and humbled our understanding. But it has also reminded us why we explore, not just to find answers, but to continually expand the boundaries of what we believe is possible. There really is no going back now. The universe we thought we knew has been replaced by one that is older, more structured, more efficient, and far more mysterious than we dared to imagine. And that realization is both terrifying and profoundly beautiful. Thank you for joining me on this long, detailed journey into one of the most important discoveries of the JWST era. What do you think this primordial galaxy means for our understanding of the early universe? Does it require new physics, or can the standard model still be adapted? Drop your thoughts in the comments. I read every single one. If you love these extended, deeply researched explorations into galactic origins and the biggest questions of cosmology, please hit like, subscribe to Galactic Origins, and turn on notifications so you never miss an episode. This is Galactic Origins, uncovering the birth, evolution, and mysteries of our universe. Until next time, keep looking up with curiosity and courage.